In this video series, we will be discussing both derivatives and all of the key features that will culminate to be able to allow us to graph the function f of x based off of everything we know from calculus. So to begin, we do need f prime of x and f double prime of x. I would highly encourage you to go ahead and pause your video, attempt to find these on your own, and then make sure you have it correct. So we have low times the derivative of the high, which would be 4x minus 2 times x squared minus 9 times the derivative of our denominator all over x squared minus 4 squared. So now we do need to go ahead and combine what we know. So we have 4x times x squared minus 4, so that's 4x cubed minus 16x minus, so we're distributing 4x throughout, so that's 4x cubed plus 36x all over x squared minus 4 squared. So our 4x cubes canceled, and then we're left with 20x over x squared minus 4 squared. So that is the first derivative. So then we also need the second derivative, which we'll use quotient rule again. So that's 20 times x squared minus 4 quantity squared minus 20x times, so we have 2 times x squared minus 4 times 2x, the chain, all divided by x squared minus 4 to the fourth. And we have, as we usually do, a GCF of 1x squared minus 4 throughout all of this. And that GCF occurs because of chain rule. So now we can distribute and simplify. So we have 20x squared minus 80. And then in the back we have 40x times 20x, or negative 80x squared. It's all over x squared minus 4 quantity cubed. So then that gives us negative 60x squared minus 80. Or we could really factor out a negative 20. That might help a little bit. Not exactly sure if it'll help a ton, but we may as well go ahead and factor that out just so we know what we're looking at. So we're looking at 3x squared plus 4 when we factor out a negative 20, all divided by this mess. So now we should start out by finding x-intercepts, y-intercepts, and then we'll use our derivatives to help us out. So the x-intercepts. So we find x-intercepts by setting the numerator equal to 0. And we get negative 3, 0, and 3, 0. Y-intercepts, they come from plugging in 0 into our function. If we were to plug 0 into our function, we get 0 and 9 halves. Next, we need to talk about vertical asymptotes versus wholes. So wholes are common factor, vertical asymptotes are singular factors that don't cancel out of the denominator. So our restrictions are plus or minus 2, and that doesn't factor out, so therefore they're vertical asymptotes, so we have none for our wholes. Horizontal asymptote. That all deals with the degree, as we discussed in previous videos. So the degree matches, so it's a over b or 2 over 1. So y equals 2 is our horizontal asymptote. Now we finally get to the information from our derivatives. So we need our critical numbers. So our critical numbers be x equals 0 and plus or minus 2. And then we have possible points of inflection, and that's plus or minus 2. Now, this is actually a restriction because of our vertical asymptotes piece. So technically we need to include it on our table, but we do need to make a side note that it's not actually a possibility to be a point of inflection or an absolute max or sorry, a relative max or min. So we will throw that off the table. So then we should discuss domain, and that's all values of x such that x does not equal plus or minus 2. Another way to say that is negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Totally up to you on which way you want to go. Symmetry-wise, so even or odd. This is an even function, which means it has y-axis symmetry. And we know that because if you plug in f of negative x and negative x in, you get 2 times negative x squared minus 9 all over negative x squared minus 4. This is all from pre-calc, and that should be 2 times x squared minus 9. It's going back to the original function. Therefore, it's even because it's the original function. So it's even, therefore has y-axis symmetry. So then we need to go ahead and figure out our intervals for which we want to test. So we have a whole slew of values. So we're going to have our test pieces. From our test pieces, we're going to have the interval negative infinity to negative 2. And then we'll go from negative 2 to 0. But then we need to stop and test x equals 0 because it's not a restriction like negative 2 was. And then we'll go from 0 to 2, and then 2 to infinity. And again, we're not stopping at 2 and negative 2 because they're restrictions on the function, so we can't actually test any pieces along it. Now from this, I will have testing points for a few things. So we'll have f of x, that will be very limited, f prime of x, f double prime of x, and then our conclusion. So we're talking, when we look at f of x, we're talking function value. We can only find a function value if it's an x coordinate. We can't find a function value over an interval. And then when we're talking about prime and double prime, we're discussing our rules for increasing, decreasing, concavity, all of that. So we can't test an interval on the function, but we can test an x coordinate, x equals 0, and that's our y-intercept of 9/2. We already found that piece. So this is 9/2. Sorry, I still had the drawing mechanism turned on. So now we need to go through and answer the rest of our questions. So if we were to plug something in the interval of negative infinity to negative 2, let's say negative 3 for the sake of argument. We plug negative 3 into f prime, we should get a negative. And if we plug negative 3 into double prime, we should get a negative. So if f prime is negative, we know our function is decreasing. And because double prime is negative, we know it's con down. Now we're not going to justify this because we're using it within a table and then we're going to sketch our function. I'm just trying to get some decent pieces from this. So then at negative 2 to 0, so let's say negative 1. Prime of negative 1 is a negative and double prime is a positive. So now we know we're decreasing, but yet we're con up. At 0, prime is equal to 0, which makes sense because it is a horizontal tangent, therefore it should equal 0. Now, if we plug this into double prime, we get a positive. We plug 0 into double prime, we get a positive. And because we get a positive, or that it's con up, and this is a possible point of extrema, we now know that this is a relative minimum because it's concave up at 0, and it's a critical number. 0, 2. So 0 to 2, let's test 1. F prime of 1 will give you a positive, and for double prime, a positive. Because it's a positive, we know that we're increasing and we're con up. So now 2 to infinity. So let's say 3. Prime of 3 would give you a positive. Double prime of 3 would give you a negative. Therefore, we're increasing and con down. Now that we know this information, we're going to now put all of our conclusions onto a graph. So let's go ahead and bring up a new sheet, and let's get our grid going. So I have my grid going here, and we have our y-axis and our x-axis. So then we know at 2 and negative 2, we have vertical asymptotes. So we know that we have key features of vertical asymptotes at negative 2 and 2. And then we also know that we have a horizontal asymptote at 2. So we know we have a horizontal asymptote at 2 running across. So we have all of our asymptotal behavior graphed. We also know that we have a y-intercept at 9/2. So that would put us roughly here in the middle. And then from that split point at 0, that's our relative min, we know that from negative 2 to 0, we're decreasing and concave up. So if we're decreasing and con up, that'll look like that, but it shouldn't go below our point. I'm sorry about that. And then we're increasing and con up on the interval from 0 to 2. So we have that portion sketched. We also know that at 3 and negative 3, we have x-intercepts. And then on our interval from negative infinity to negative 2, we know we're concave down and decreasing. So if we're concave down and decreasing, our function is going to roughly look like this. And because we know we have symmetry across the y-axis, we know that it has to look like this on the other side, but also our information indicates that we're concave down, but yet increasing on the interval from 2 to infinity. So that makes sense. This is the first piece of curve sketching without a calculator, using all of the information from our derivative tests. Make sure this is starting to click. Ask questions. If it's not, happy to help you. I will be recording another video. Thank you for taking time to watch this. I appreciate it.